Hi everybody, welcome to video 9. You can probably tell this is more stoichiometry practice. And this is actually going to be the practice that goes with homework sheet number 1. So Stoic homework number 1. I'm going to do the first page and then you guys are going to do the second page. So homework sheet number 1 begins with many household chemicals form dangerous toxins if mixed together and allowed to react. For example, bleach, which is NaClO. So we're going to be dealing with NaClO, and ammonia, which is NH3, can form chlorine gas in the following chemical reaction. Now, while I'm writing this, I do want to talk about, so this chemical reaction can happen. We worry about it more at places like pools, which have very concentrated forms of ammonia and bleach. So this can happen with household chemicals, and you never want to mix household chemicals, but we also worry about this chemical reaction a lot at pools. NaO, that's an N. Sorry. NaONH3 and Cl2, which is going to be that chlorine gas. So if you mix this, which is bleach, with this, which is ammonia, you can run the risk of producing chlorine gas in your home. And we worry about this especially a lot at pools or other different industries which use very strong forms of bleach and very strong forms, especially of ammonia. So we're going to be working with this chemical reaction. When you balance it, you figure out it's pretty much all 2s except the last Cl. It's only 1 Cl2. So these are the common names. This is the equation and this is the balancing. Now, what I would do before I even started, I would figure out what in the world are the atomic masses. What are going to be the molar masses? I would get out a periodic table, and before I even read the equation, assume you're going to have to calculate them all. So NaClO. Na is 22.98. So we can round 22.98 would round up to 23. Plus chlorine is 35.45. Plus oxygen is 15.9 or 16. So NaClO has an atomic mass of 74.45. NH3, nitrogen is 14 plus hydrogen is 3. That one's pretty standard. That's 17. NaONH3. Sodium has an atomic mass of 22.98, so that one was 23 plus 16 plus 14 plus 3. So that has an atomic mass of 56. Cl2, chlorine has an atomic mass of 35.45, so an atomic mass of 70.9. I would figure out the formula masses right away just so you have them. Equation, common names, formula masses, we are ready to start. Now, we are going to assume that this is not a floor. The problem says you mix 50 grams of bleach with excess ammonia before you remember that this is a very dangerous chemical reaction. How many molecules of chlorine gas did you make? So we are going to start our problem knowing 50.0 grams of bleach are mixed with excess ammonia. And the first thing you are asked is, how many molecules of chlorine gas did you create? So start with what you know. What do I know? I started with 50 grams of bleach. Bleach is NaClO. Using our mole conversions, grams is not usually a helpful place to be. Go to moles, grams of NaClO for moles of NaClO. 1 mole of NaClO contains 74.45 grams. Now that I'm in moles, I can switch to another compound. So from moles of NaClO, I can go to chlorine gas. Using my mole ratios, I know that for every 2 moles of NaClO used, 1 mole of chlorine gas is going to be produced. And I was asked to go all the way to molecules. So grams to moles, you get a lot of practice with that one. You know that's molar mass, but it's important to remember moles to molecules is that Avogadro's number. So 1 mole is 6.02 times 10 to the 23rd molecules of Cl2. All that's left is to get it in your calculator. So 50 divide 74.45 divide 2 times 6.02 times 10 to the 23rd, and you are left with 2.02, right? 3 sig figs? Yep, 3 sig figs. 2.02 times 10 to the 23rd molecules of Cl2. So your dangerous chemical reaction created 2.02 times 10 to the 23rd molecules of that chlorine gas. So that's the amount of gas you released in the air. Next thing I want you to calculate is how many grams of the salt of that NaONH3 will be produced. Starts out the same. Begin with what you know. So we technically could use this as a known. I always go back to what you were given in the problem because you know that was right. There could have been a miscalculation here, but you know that this was right. So we know that there are 50.0 grams of bleach, which is the NaClO, going into a reaction. Now you're going to notice these get repetitive because remember, it's the same up until you switch to a compound. From grams to moles, so grams of NaClO to moles of NaClO. 1 mole contains 74.45 grams. From moles of one substance to moles of another. This time we're going to the salt, so NaONH3. From moles of the salt to grams of the salt. Mole conversions: for every 2 moles of the bleach used, there are 2 moles of the salt produced. This is just grams to moles as a molar mass. For every 1 mole of the salt used, there are 56 grams of the salt. Then type it into your calculator. 50 divide 74.45 times 2 divide 2 times 56. You have made and need to clean up 37.6 grams of the NaONH3. So given the amount of bleach produced, we have figured out, given the amount of bleach you started with, we have figured out how much salt did I make, how much gas did I make. Now, to throw a little bit of real world application in you. Problem 3 states that chlorine gas is deadly at concentrations higher than 1 kilogram per liter. So Cl2 is deadly at concentrations of 1.0 kilogram per liter. Your kitchen has a volume of 1.67 times 10 to the 5th liters. You need to calculate, would this mistake be deadly, or would it not be deadly if all the chlorine gas was produced? Again, start with what you know. This is just going to be a slightly different problem. So, what do I know? I know that I have 50 grams of the NaClO. Now, we know that these 3 steps are going to be a copy because I'm going from bleach to chlorine. So that one, that's just going to be recopying it. I'll explain it as I copy it still. So I'm starting at grams of NaClO. From grams, I can go to moles. Using that mole ratio, 1 mole contains the 70, I'm going to run out of room, 75 grams. From moles of bleach, I can go to moles of gas using my coefficients, so using my red numbers. From moles of gas, now we got to notice our labels. I need to get to kilograms per liters. So from moles of Cl2, I need to go to grams of Cl2. And I already calculated that. 1 mole, that we said that was 70.9 grams. And then from grams, I need to get to kilograms. So that would be from grams of Cl2 to kilograms of Cl2. Using my green sheet, I know that 1 kilogram contains 1,000 grams. Now, this is where this problem gets a little bit different. Density is actually my end goal because I'm trying to compare my density to a deadly density. So do the calculation to solve for kilograms. So 50 divide 75 divide 2 times 70.9 divide 1,000. I created 0.0236 kilograms of Cl2. To determine if it's deadly, I need to compare a density. Now, I created 0.236 kilograms in this volume of space. So take your kilograms, divide by your volume of your kitchen. So this number divided by 1.67 times 10 to the 5th, and you get a very, very small number, 1.4 times 10 to the negative 7th kilograms per liter. Now, 1.4 times 10 to the negative 7th, much smaller than 1.0. So the answer would be no. This would not be a deadly combination given the concentration of gas produced and given the mass of gas produced and given the volume of your kitchen. Now, I want you to do the second page of this sheet on your own. It's the same type of thing. It's talking about combining 2 chemicals, creating a gas in a chemical reaction. This equation is a little bit bigger, so I already balanced it for you. And the last step is very similar to this one. Calculate the molecules, divide by, nope, actually the last step is a lot easier. So it's very similar. Calculate the molecules, compare what you got to the number you should get, and then see if your deadly gas killed you. But go ahead, do that second page on your own, and then you'll check your answers with those checkpoints.